The Mojave Desert, Nevada, USA. A hot, dry and desolate place. It's mind-boggling to discover that in the middle of this dusty desert is one of the most extraordinary and exciting cities on Earth. Las Vegas. An artificial oasis in the desert. It's one of the biggest electrical extravaganzas in the world. "30 million people visit Las Vegas every year. It's a city completely over the top, where everything is done to excess. Visitors eat a lot, drink a lot, and above all, consume huge amounts of electricity. But the gigantic electricity bill is not just for the lights and entertainment. You can't survive out here in the Mojave Desert without air conditioning. And air conditioning uses a great deal of electricity. So where does the electricity come from to power this huge metropolis? Las Vegas was dealt a lucky hand just over 60 years ago. In 1935, one of the technological wonders of the world was built nearby, the Hoover Dam. It sparked the growth of Las Vegas. Before the dam was built, this whole area was dry for one half of the year and flooded for the rest. Las Vegas was just a dusty old town. But the Hoover Dam changed all that. It provided constant water and electricity to the surrounding areas. The Hoover Dam put Las Vegas on the map. Dam workers and their families flooded into Nevada. It was one of the few places they could get work during the Great Depression of the 1930s. When the Hoover Dam was finally finished, it tamed the great flow of the Colorado River and used the energy from the gushing water to provide endless electricity for parts of Arizona, California, and Las Vegas. The Hoover Dam spans 220 meters from its foundation to its top. The dam's generators can produce up to 2,000 megawatts of electrical power. That's 2,000 million watts. When the dam was built, the huge concrete crescent trapped the water flowing down the Colorado River to create Lake Mead. It's the biggest artificial lake in the USA. Many dams have water cascading over the wall, but here the water from Lake Mead drops down 4 intake towers. The pressure of the falling water turns the turbines that drive the generators to make electricity. Water flows down the pipes hidden in the canyon walls. It enters the building that houses the turbines and generators. The flowing water spins the turbine blades. The turbine is connected by a shaft to the generator above it. Turbines turn the generators to make electricity. The water that has been churned through the turbines from Lake Mead is finally returned to the Colorado River. You have to descend 160 meters deep down into the Hoover Dam wall to reach the generators.
We're overlooking the wing of the Nevada power plant. Now from here you can see there are 8 generators. On the Arizona side, there are 9. The turbines are located directly below the generators, 2 stories below us.
But how do the generators make electricity? A voltage is generated or induced in a coil of wire when a magnet passes through it. If a magnet rotates near a coil of wire, an electric current is produced in the wire. The rotation of the magnet produces alternating current. That means that the current is continuously changing direction.
We're on top of a 600-ton magnet that goes all the way around the generator, and it's attached to the shaft. Above and below the magnet are coils, and as the magnet moves around the coils, it produces electricity in the coils.
The Hoover Dam generators produce alternating current. That's because they have a rotating magnet which changes the direction of the current. The power output of a generator is measured in megawatts. One generator is producing 100 megawatts, which is 100 million watts. That's enough to power 1,000,000 100-watt light bulbs. The generators are directly linked by wires to transformers outside the building. The wires from the generators are fed through these silver tubes into the transformer. The voltage is stepped up from 16,500 volts AC to 230,000 volts AC. This is done to reduce the loss of energy during transmission along the lines.
Well, the power travels through these high voltage lines to the towers. Now, the reason the towers are at angles is so the wires don't touch the canyon wall. Now, tracing those wires, you can see they travel to Los Angeles, Phoenix, and Las Vegas.
The wires are divided into different directions at a distribution center. At this point, the wires are carried by great pylons perched along the horizon to the surrounding towns. It's not just the Hoover Dam that supplies Las Vegas with electricity. The company Nevada Power has many additional power stations dotted around the city, which run on gas and coal. These fossil fuels are burnt to heat water to produce steam. The steam then drives the turbines, which turn the generators to make electricity. The electric current from these power stations also flows down the overhead cables heading for Las Vegas. The high-voltage electricity arrives in Las Vegas without too much power loss. But 230,000 volts is extremely dangerous to use in homes and hotels. So it goes to a substation, where it's stepped down by various transformers, from 230,000 volts to 12,500 volts. It's then sent to nearby hotels. A little bit of ancient Egypt comes to town. This fun-packed pyramid is one of the biggest hotels in the world, with over 4,000 rooms. Its demand for electricity is like that of a small town. The Luxor offers a pharaoh's welcome to over 8,000 guests, creating a huge demand for electricity.
Okay, we get our power from Nevada Power Company. We have 2 feeds into the hotel. It comes in at 12,500 volts in cable like this one here. It comes into 2 main switches. From these switches, it goes on into a line of switches inside of this room here. And from there, it's distributed to various transformers and all around the hotel here.
The Luxor Hotel needs its own bank of transformers to step the high voltage alternating current down to various voltages.
Okay, you're seeing 3 big coils in there. That reduces the 12,400 volts down to 4,160 volts. This is the power that we use for our air conditioning units. And then it goes to another bank of transformers that breaks it down to 120, 208 volts that we use for lighting and for slot machines, gaming, and whatever else it might be.
But for the folks who don't have a home with 4,000 rooms, they don't need so many transformers. One is usually enough to get yourself hitched to electricity. This transformer steps the voltage from the substation right down to 110 volts AC. These transformers are dotted all over Vegas, from the famous Vegas Strip to the suburbs. If it wasn't for this routine of stepping up and stepping down, most of the electricity would be lost before it got to Vegas. Electricity is generated at 16,500 volts AC, stepped up to 230,000 volts AC by a transformer and sent long distances down the power lines. Then it's eventually stepped down to 110 volts AC before it gets into homes. But why bother to step the voltage up and then down? 230,000 volts is extremely dangerous. Stepping it down to 110 volts AC is much safer. But why step it up in the first place? Why not just generate and transmit the alternating current at a much lower voltage? If they did that, there'd be a big problem. To transmit electricity at low voltage, the current has to be high to compensate for the low voltage. And high current heats up the wires. This is an infrared image of the wires at low voltage AC. They appear white because they're hot. With high voltage and therefore low current, the wires barely show up because they're not so hot. Heat wastes energy, so if we transmit it at low voltage and high current, we would end up with less electricity reaching our home. So, if heat wastes energy, then surely the lights of Vegas must consume vast amounts of electricity.
By looking around the city of Las Vegas, one would think that the energy consumption of all the neon lighting in Las Vegas would just be incredible. Quite frankly, though, they found out several years ago during the energy crisis, they initiated a provision that all the hotel casinos would have to turn off their lights at a certain time in the night. What they found out by this after a period of doing that is that the actual power consumption of the lighting around Las Vegas was only the equivalent of about 2%.
These two bulbs are both producing the same amount of light. The filament bulb is a 15-watt bulb, but the neon light is only 5 watts. Using an infrared camera, we can see that the filament bulb on the left is producing more heat than the neon light. So the filament bulb is wasting electricity by producing heat.
The filament type lighting, which produces a lot of heat, is a lot less efficient. To put that a little bit into perspective, if you were to take this 4-meter section of neon, it would be approximately the equivalent of about one 100-watt light bulb.
Neon lights work in a completely different way to ordinary filament bulb lights. The crucial difference is that neon lights don't have filament wires that glow white hot. If there's no filament in neon lights, how do they glow? Once the hoteliers have decided on the look of their neon light, work can begin on a new neon light creation. Electrodes are fixed to the glass tube at each end. These allow the electric current to flow through the gas, causing the gas to glow. The glass tube is gently manipulated over a naked flame to produce a shape. Air is continually blown into the tube to stop it squashing as it bends. The hot glass is so flexible that it's easy to bend into a design. You can use clear or coloured glass, whatever takes your fancy. A pump is used to remove all the impurities that might have got trapped inside the glass tube. The tube is heated using a high voltage AC supply to shift any remaining dirt. The tube is then left to cool down. The tube is filled with neon gas. A rainbow of colours can be produced by using different gases. The colours are produced when the current flows through the gas. Argon gives purple. Neon gives red. Helium, very pale blue. Krypton, silvery white. And xenon, deep blue. Put the gases in coloured tubes coated with chemicals and we can produce more colours. A blue glow in a white tube gives white light, but red glow in a white tube gives tangerine. Las Vegas owes its very existence to the Hoover Dam. If it wasn't for the dam, this whole area would still be a barren desert. Like all big cities, Las Vegas is not environmentally friendly, but the Hoover Dam doesn't contribute to the general atmospheric pollution. Most of that comes from the cars. The advantage of using hydroelectric power from the Hoover Dam is that it reduces the total amounts of fossil fuels that would need to be burnt to produce electricity. This in turn reduces atmospheric pollution and helps to prolong stocks of fossil fuels. Coal, oil and gas will probably run out in the 21st century, but the Hoover Dam is designed to last 2,000 years.
Oh, ho, 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 ho. C'est magnifique! Le weekend starts here. That's right, I'm off to Paris. I've got my travel bag, my camera, my passport. It's a case of très chic electric. In other words, my journey today is all thanks to electricity. Now, I'm no train spotter, but I've been told that this is one of the most advanced electric trains in the world. Here in London, it runs on 3 rails, the third one supplying electricity to the motors. Those motors have to cope with 3 different voltages as it travels from London to Paris and London to Brussels. Believe it or not, this train is 1/4 of a mile long with an electric power car at each end. Sandwiched in between are 18 passenger cars, and it can carry about twice the number of passengers as a jumbo jet. Oh, hello there.
Hello, welcome to the 953. I'm Bob Priston, the driver.
Thanks very much. I'm Jason Bradbury, your passenger. I tell you what, Bob, I feel like I've already walked to Paris. You haven't got a glass of water, have you?
Not here, but hey, try the buffet.
Nice
I'll be
idea.
alright.
See you later.
Okay,
Bye-bye.
cheers.
Okay, coach 7.
Fantastic. I do hope, Philippe, you'll be keeping me in a manner to which I'm accustomed.
Of course, we will. You will have a lunch on the...
Thanks very much. Au revoir.
So actually 7 is on the right, the left. Sorry.
Great.
I would like to welcome you aboard this Eurostar service. You will arrive in Paris at 14:08 local time.
The train takes 3 hours from London to Paris. It travels at 186 miles per hour, that's 300 kilometres an hour, and it's got the power of 20 Formula One cars. And it'll take 1.5 miles to stop. How about that? Oh, Philippe, hello.
Morning, sir. How are you?
I'm very well, thank you very much.
What would you like to drink with your starter?
Orange juice, please. Oh, excuse me, jus d'orange, s'il vous plaît.
Okay, I'll bring you some later.
Merci.
Would you like some water as well?
Oui.
In a few minutes we will be entering the Channel Tunnel.
Ooh, here we go. Hold your nose. This Eurostar train is basically 2 trains in one. It's got a power car at each end, and if you split it in the middle, in an emergency you can put all the passengers in one train and get them out safely. Brilliant. Well, my little techno train has delivered me safely and swiftly into France, and with it has come a change in electrical system. Before we were using DC, that's direct current, provided by a third rail. You see there's only 2 rails there now. Now though, we're on AC, that's alternating current. That comes from those cables up there.
Ladies and gentlemen, we will shortly be arriving in Paris, Gare du Nord, where this train terminates.
Great! Here I am in the Gare du Nord in Paris. Time to find myself some croissant. Smashing. Well, I'm in this great city, but I need a motor to get around, and it's just got to be electric. I'm sure I put it around here somewhere. Aha! How are you, sir?
Laurent,
Laurent.
Jet Paris, pleased to meet you.
Pleased to meet you, Jason. What have you got here?
This is your electric car.
My electric
For some
car.
hours, you will enjoy it.
Fantastic. An electric car, so how do you get the electricity into it?
Very simple.
Let's have a look.
Just have a look. You just open this door,
Yep.
just plug this special
Socket.
socket,
Yep, into the socket there.
and then plug it.
Let's have a look. Where do you plug this thing?
You plug it in the socket that you will find all around
All over the city?
the city. I have here the plan for you, where you can
superb.
find...
This is where I can find the electricity points, yeah?
Exactly, but you could as well plug it at your home.
Oh,
Like on
superb.
the,
Bit of a long
the
way,
plug of
though.
the fridge. It's a long way for you, yes, maybe.
So what have we got here then?
So this looks like a normal car,
Yep.
except that this is an electric engine.
In fact, this is a DC, direct current motor, because it runs on batteries which can only supply direct current.
Okay, I understand that. Oh, there's a battery there. Oh, surely that small battery doesn't power this whole engine.
Not at all. This battery is like in another normal car,
Right.
just for the headlamps of the
peripheries
electric
and so on.
window. Yeah,
I tell you
exactly.
what, if you don't mind, I've got another little electric bit of kit. I'd just like to take a close look, if you don't mind.
Well, what are you doing? Wait a minute.
Oh, don't you want me to do that?
No, I'm
Well,
not sure that will be the best idea.
Oh, okay, that doesn't matter because it serves a good purpose anyway. This is another electric motor. It also uses DC, direct current, and it works in exactly the same way. See, its constituent parts are exactly the same as the ones in that big motor that drives the car. You see, it's a typical DC motor. In the centre are the coils of wire. So press the button there, you see the power goes through and it starts spinning around. That, of course, is surrounded by a magnet which goes all the way around the outside there. At the back here are the brushes, and they, of course, touch the copper commutator right in the centre there, which again spins if I press the button.
Batteries only supply direct current, so motors that run off batteries are DC motors. They have 2 permanent magnets, a coil of wire which is free to spin, and two electrical contacts called brushes. These touch a split ring commutator which allows the current to flow through the coil of wire. For simplicity, only one coil of wire is shown here. It appears white when a current flows through it. While current flows, the coil of wire becomes an electromagnet, with a red north pole on top and a blue south pole on the bottom. Because north attracts south, the red face of the electromagnet attracts the blue face of the permanent magnet. Also, red repels red and blue repels blue. This push and pull between the electromagnet and the permanent magnets makes the coil turn. As the electromagnet moves through the vertical position, it turns off and on. This switching mechanism ensures that the top part of the coil is always red and the bottom blue. The push and pull between the electromagnet and the permanent magnets is always in the same direction. So the coil continues to rotate.
So what kind of performance do you get out of this motor?
With this motor, you can drive 90 kilometers per hour.
Right.
And the batteries allows you to drive 80 kilometers.
And then you've got to recharge the batteries.
And then you get to recharge the batteries. It will take 6 hours.
Yeah. Unless
you recharge it to a rapid charger, will allow you to charge for 1 hour.
1 hour. Can I have a look at the batteries?
Sure, the batteries are in the back of the car.
Wonderful. Let's have a look. Aha! Oh, I see. So the batteries are located under here.
Okay, now I think it's time for you to test the car.
Sounds great. So you're going to show me the ropes?
Exactly.
Good man. Right.
And here is your energy meter, and as soon as you will drive, then the energy meter will go down because you will use power.
Yeah. Fantastic. Well, I'm ready for my quiet trip around Paris.
Okay, so Jason, enjoy it.
Bon voyage.
And see you soon in Paris again.
Sounds great. A bientôt. Bye-bye. Right then, there we go. I'm off. It's testament to the effectiveness of this car with regards to how environmental it is that on certain days in Paris the pollution gets so bad they stop the traffic coming in on alternate days, except of course this little beauty. You can drive around in this whatever the pollution in the city. Of course this car is not without pollution. The electricity comes from somewhere. It's just that the pollution is centralised around the power plant where it all comes from. Obviously as I put my foot down the accelerator I use up the power, but if I release my pressure on the accelerator, look, it goes into the plus. It actually recharges the batteries. The motor's not being so much like a motor, more like a generator in fact.
An electric motor can be turned into a generator. Instead of the electricity making the motor turn, the movement of the coil can make electricity. When the current is turned off, the rotation of the coil makes the bulb light up. When Jason takes his foot off the accelerator, it cuts the electricity to the motor. But because the car is still moving, that movement is used to generate electricity, which recharges the battery.
Another great feature of this electric car is its energy efficiency. Believe it or not, a petrol engine is only 30% efficient. This little baby, 80% efficient. Well, there are only two ways up there, foot power and electric power, by which I mean, of course, the lifts. And I know which one I'm taking. Electric motors aren't just used for travelling in cars and trains, they're also used for going up and down. And thanks to electric motors, I've now made it to the top. has just one snag with this electric car. After 80 kilometres, it needs a 6-hour recharge to get it back to full capacity, which is a tad inconvenient. Right, that's it for me. All I've got to do is fill her up. Simple operation. That's it, I'm off for a croissant. Oh, and another form of electrical transport. Can you imagine what it would be like if the metro ran on diesel motors instead of electric ones? The tunnels would be full of smoke and pollution. Unlike the electric car, the Eurostar train doesn't have to carry its power, and it certainly doesn't need to be left on charge through the night. No, it gets its power from that third rail and the overhead power lines. With such a massive European effort involving Belgium, France and the UK, it's not surprising that there are a number of problems to iron out, not least the different electrical systems. 25,000 volts AC in France and in the tunnel, 750 volts DC in Britain and 3,000 volts DC in Belgium. So how do the motors cope with all this switching about between AC and DC? Well, I'll tell you what, I don't know, but I know someone who does. Allow me to take you to the North Pole. Well, here I am. It took me 2 weeks to get here. I finally arrived at the North Pole. All right, it's not the North Pole. It's actually where they look after the Eurostar. And I've got to find someone called Joe. Just look at this baby. 0 to Paris in under 3 hours. Now, where is Joe? Hello? Oh, hello there.
Hello.
Hi, Joe. Can I come and join you under there?
Yeah, definitely.
Smashing.
Well, I just put that on a bump cap on your head.
Not a problem. Okay, does it clash? Is all right?
Lovely.
Spot on, thank you. Oh, excuse me. Right, Joe, where's the motor? Because that's what I'm here to look at.
Well, this is our motor. It's an AC motor.
An AC motor. Why AC?
Well, it means that it's low maintenance. You haven't got any brushes or commutator.
AC motors don't have brushes. And in this example, it's not the coil rotating, it's the magnet. As alternating current passes through the coil, it in effect becomes an electromagnet. One end becomes a north pole and the other a south pole. Because alternating current goes first one way, then the other, the position of the poles keeps changing. This produces a pulling and pushing effect with the permanent magnet, and the magnet rotates.
Right, Joe, what have we got here?
This is our AC motor that we've just seen under the train.
Yeah, okay, it's minute.
Yeah, it is. We've got...
You're not telling me that 12 of these power that entire train all the way to Paris?
Yeah, well, that's one of the advantages of having an AC motor. You get a very high power-to-weight ratio.
And what's power-to-weight ratio when it's at home?
Well, it means that we can produce a lot of power, but still have a very, very small motor.
Fantastic. What other advantages does this particular motor have?
As you can see, it's all encased. There's no parts that you can actually see to get into. All we've got is a core around the outside with a rotor in the middle.
Yeah.
There's no actual physical contacted parts like you get on a DC motor. There's no brushes, no commutator.
So how does this engine deal with all the different electrical systems?
Well, we've got a series of transformers and converters in the power car.
That's the cue I need. Get over here and get a load of this. This is my little model railway. What do you think?
Excellent. What more can I say?
Absolute replica of the Eurostar. It also works in a very similar way, doesn't it?
Yeah, we've got 240 volts coming in from the mains.
Yeah.
That's AC. Got a transformer where it's transformed down to 15 volts AC. And then this box of tricks here is our converter, where the AC is converted into 12 volts DC for the motors on the model train.
Fantastic stuff. So it's working exactly the same way as the Eurostar, except that starts off with 3 different voltages, which are then converted, ending up with AC that works the motor in the train.
This is the inside of a transformer. It can change the voltage up or down, depending on what the motor needs. The motor in this model train needs only 12 volts DC, compared with 240 volts AC provided by the mains. Inside a transformer there are 2 tightly wound coils of wire wrapped around a soft iron core. The right-hand coil has more turns of wire than the left-hand coil. Electricity enters the transformer from the right, with 240 volts AC across the coil. It emerges from the left at 12 volts AC across the coil. It's stepped down from 240 volts AC to 12 volts AC. That's because there are 20 times fewer turns of wire in the left coil than the right, so it's stepped down 20 times. The Eurostar also has lots of transformers and converters, which ensure that its motors always get the right supply of alternating current, whichever country it's in.
Well, I'll tell you what, I can drive this one okay, but I'd like to have a chance of driving the big one.
Yeah, come on, see what you can do.
Thank you.
Right, Jason, we come out into the power car.
Excellent stuff.
At the front we've got the driver's cab.
Oh, it's like conquering Everest. Hang on. I'm in.
Come on, Jason, come on into the Eurostar cab.
Oh, great. Can I sit in the driving seat?
Yeah, help yourself.
All right. How about the throttle? Where's that?
Right, this is our knob here.
Okay.
Leave it. Do you want to have a play?
Yeah, absolutely. How do I put the power on?
Push it forward and we go faster.
Brilliant. And what about braking?
Well, if you put it back the other way,
Right,
we're going to
right.
electric braking.
Oh, stunning
Slowing
stuff.
down.
What about the different electrical systems that we encounter? How does the driver switch between those?
Well, we're doing, say we're going from London to Paris.
Yep.
The driver would use this knob. Okay, so we're going to put it onto the BR system, the 750 volt DC. And the Eurotunnel, put it onto the ET mode, the 25,000 volt AC mode. And then we're going into Paris. We're coming on the high-speed French line, 25,000 AC.
And just to make it really complicated, if I wanted to go to Belgium, what would I do then?
Same knob.
Yeah, all the way around.
All the way around, and we're in the Belgium system. The 25,000 volt AC pantograph will go down. We have another one going up, the 3,000 volt DC.
God, it's complicated, isn't it? But I tell you what, not half as complicated as the stuff back there that I believe converts between these systems. Can we have a look?
Yeah, come on out and I'll show you.
Brilliant. Thanks, Joe.
Come on, Jason.
The AC motors might be small, but it takes all this electrical equipment, which includes transformers, just to ensure that the various AC and DC power supplies from different countries can be changed to 1400 volts AC to drive the motors. You've done me proud, but I've got to rush off. I've got another electric motor I've got to have a play with. Thanks a lot.
Okay, cheers.
But this is my favourite little motor, DC, of course.